kind of ambivalent on it. What do you guys think? All right, we'll go with that setting. Geez. I'm not really sure what they mean. Anyway, but seriously, my roommate can hear you. My uncle in another state can hear you. Okay, so I think you'll agree before we can actually get to drawing chemical structures. Oh, does this mean I can walk and talk at the same time? That would be awesome if so. Good. It's not clear. I'm not sure I get their meaning. Anyway, before we can get to drawing structures, which I'd like to sort of at least, you know, end on today, and we'll probably pick up there on Monday. Before we can get there, we have to have molecules, and before we can have molecules, we have to have atoms. And I'm going to take it for granted that in Gen Chem you learned about atomic structure. You learned that an atom of any given element consists of a central very massive nucleus that's positively charged, right, containing positively charged protons and uncharged neutrons, and nearly all of the mass of the atom is in the nucleus. And distributed around that nucleus in some sense, in these things that we call orbitals, that are regions of space that are essentially probability distributions of finding electrons in that area. In some sense around that nucleus, all of the electrons are going. And electrons are negatively charged and of very, very little mass. Keep this class running, OMG. Oh, chat, you're hilarious. Anyways, so I take it that you've heard about all that. I don't think we really need to get too concerned with any heavy-duty molecular orbital theory. I mean, at the same time, we want to be educated adults. You know, I would say if you have a notion of the atom looking like the solar system with the electrons rotating or revolving around the nucleus, that's probably not quite adequate. That planetary model was largely believed until the earlier part of the 20th century, but now we understand that's a little bit overly simple. But if instead you're just of the idea that in some sense, in some regions of space around the nucleus, the electrons are flying around, that's probably close enough. With that comes the idea of knowing what you're looking at when you look at the periodic table. And by the way, that's another thing I want to be sure to mention. With every exam, I will always give you a periodic table. You need never worry about that. I wouldn't dream of giving a chemistry exam at any level, freshman, sophomore, junior, senior, without providing a periodic table. That would be flat out immoral. So you don't need to worry, you'll always get a periodic table. It'll probably look much like the one I put in your class notes. I have one here somewhere. There it is. I just want to make sure the chat can see it. So strangely, I have to get chat out of the way so the people present in person can see it. This screen is really postage stamp sized. Well, I can maybe at least close one of these windows, then maybe that'll free up some of the hamsters in spinning in wheels over here. I take it everyone's registered their attendance who wants to. It doesn't matter. It's not counting for a grade today. So I think we can, that's not good. End class session. End class, good. Yeah, let's at least close that. So at least that won't be in the way. Okay, so here is a periodic table. And so I assume this is something you've seen before, having taken Gen Chem. This also brings up the idea, so I talk about atomic numbers. The atomic numbers are these integers that are on the, ooh, this periodic table's busy. It's like showing me metalloids and transition metals. Look at all this. It's pretty amazing. Be that as it may, the smaller integer numbers here are going to be your atomic number that will correspond to the number of protons in the nucleus. And I think I said in the class notes that atomic number uniquely determines the element, which means that it goes both ways. For example, an atom with 6 protons in its nucleus will always be an atom of carbon, no exceptions. And likewise, every atom of carbon will have exactly 6 protons in its nucleus, no exception. That's what we mean when we say that the atomic number and the identity of the element, the atomic number uniquely determines the identity of the element. The implication goes in both directions, if you will. And then these other numbers here are weighted averages that we use for atomic masses. It's an average of all the masses of the different isotopes. And again, I'm flying over this pretty quickly because this is part of any standard Gen Chem curriculum. While we have the periodic table up, I will also mention another thing that I take it for granted that you covered is electron configurations, all that fun 1s2, 2s2, 2p6 stuff that you loved so much. I think it would be, I certainly would expect that you could write electron configurations for the main group elements, the S block, and here is the P block. Those are generally pretty straightforward. I would never dream of asking anyone for an electron configuration of one of these F block elements, these rare earth elements, because I don't know them. They are loaded with exceptions, and I don't see any value in learning them. The D block elements, though, these transition elements, those in a sense have exceptions also, except it's at least regular all the way down the column. So for instance, you might recall that the chromium column, CR is chromium, these look like they should be D4 because they're 4 slots over, but they're actually D5 because they steal an electron from the S subshell. Because when the D subshell is half filled, it lowers the energy. So chromium we would have expected to be, let's see, all of the argon electrons, 4s2, 3d4, but it's not. It's 4s1, 3d5. It steals an electron from the S's. But that's the same for molybdenum and tungsten. So that at least is regular. See, the exceptions in the F block are not regular. They're all over the place. A similar thing happens in the copper column. We would expect these ones to be D9, but they're actually D10. So for instance, silver, Ag, I guess would have your krypton electrons followed by 5s1, 4d10, right? So it steals an electron from the S subshell. So, I mean, I don't know how much we'll need those, but it could be useful to know how to do that. I would hope you could also write electron configurations for simple ions, Cl minus, you know, Mg2 plus, things like that, I think would also be reasonable. So I'm not going to go over it in particular. If you need to review those, please do. I think we'll get a chance to practice that on OWL as well. Now, does that mean it could be on the exam? Yes, absolutely. It's fair game for the exam. It's something that was covered in Gen Chem. Now, out of the 150 points of the exam, am I going to make 80 of those 150 points electron configurations? No, not so much. I hope I'm a little more reasonable than that. But certainly a couple of questions would be fair game, I would think, something like that. But other than that, I think that's all we need the periodic table for just now. Mostly we're going to be looking at carbon, as you know. Good, so let me go back to our class notes. Let me bring chat back in. I'm going to have to review it. That's fine. You know, that's what this class is for. There's certainly plenty of time. We're just getting started. So that, I think, gets us through the periodic table stuff. I also want to get us at least up to date. And again, if you need to go back and review some of these things, that's totally fine. Oh, I should say this too. If while you're reviewing some of these things, you have questions that you want to bring me during office hours, please don't hesitate. I'll be glad to help. That's what I'm here for. I'm just not going to reteach Gen Chem in any great detail during our class time, but I at least want to use this class to point you guys to those things you had in Gen Chem that were the most important for this class. Bonding is pretty important. And there's a couple different ways to think of bonding. Luckily, and I think one term that's going to come up later in this chapter is the valence bond method, or the valence bond theory, which is one of, probably two different things today, at least, that I'm going to get to that I think they make needlessly complicated in Gen Chem. I often get irritated with things like this. It just bothers me when they make something complicated that isn't. It's, you know, they purposely make it hard to understand when it's really not a big deal. And the valence bond theory says the following about bonds. It says, if you bring together two particular atoms, whatever they might be, then there is some ideal distance apart that we get those two atoms from one another, where all of the repulsive forces, like, right, because like charges repel, opposite charges attract. So, you know, there's nuclear repulsion because they're both positively charged. There's electron-electron repulsion because they're all negatively charged. But at the same time, there's attractive forces between the electrons in one atom and its nucleus, and also the electrons in one atom and the nucleus of the other. And so there's some ideal distance at which all of that balances out as well as we can hope, and we call that the bond length, or bond distance. Now, that being said, I very quickly want to add that you mustn't think of molecules or bonds in molecules as being these stiff, rigid things like that camera or like pieces of furniture. Molecules are in constant motion. Bonds are always vibrating. The whole molecule has vibrational modes. It's tumbling through space. There's rotational modes. It's traveling through three-dimensional space also. And all of these things relate to light, in fact. They relate to electromagnetic radiation. Different types of light excite different types of transitions. But even with all that, there's some at least average distance between those two atoms. That's the ideal distance, and we call that the bond length. And maybe the bond vibrates around that, but on average, there's an ideal best length. So that's what we mean by the bond length. Now, you can find a table of bond lengths, probably in your textbook. I know there's also a table of bond energies there. Of course, I do not expect you to memorize all that, please. I cannot think of a worse use of your time than that. Likewise, you'll find all kinds of tables in your book. There's a table of electronegativity values, Pauling electronegativities. Of course, you don't need to memorize those as well. One thing you'll learn about me pretty quickly, I hope, is I'm not in general a big fan of making students memorize lists of numbers. I just don't think that's a good use of your time. If on one of my exams you ever needed any of those numbers, I would give them to you. I don't expect you to flat out memorize them. Nevertheless, certainly take a look at those tables. You'll learn something. You'll learn about which bonds are longer than others, other things being equal. And you'll conclude probably that those bonds that are longer are weaker, and those bonds that are shorter are stronger, other things being equal. And if you made that guess, you would be absolutely right. You would find a similar feature with bond dissociation energies. It always requires energy to break a bond, by the way, or you could say breaking bonds is always endothermic. And similarly, forming bonds is always exothermic, always releases energy in the form of heat. So it needs to absorb energy. It requires input of energy in order to break a bond. And when you form a bond, it always releases energy. Always. There are never any exceptions. That's always true. And now you have it down on YouTube. But forming bonds is always exothermic, breaking bonds is always endothermic, always, no exceptions. Right, so now that being said, some bonds are pretty weak, and so in order to break them, you don't need to put in very much energy at all. Like the oxygen-oxygen single bond in peroxides is quite weak. Or halogen-halogen bonds, like in Cl2 or Br2. Those are pretty weak. Yes, you need to put in energy, but not very much. Other bonds are very strong, and you need to put in a great deal more energy in order to break them. What about the nitrogen-nitrogen triple bond in N2, molecular nitrogen? Very strong bond. You really need to kick it to break that bond. But you'll find in general, I think, that covalent bonds between nonmetals are typically pretty weak, with a couple pretty important exceptions. What about carbon-carbon bonds and carbon-hydrogen bonds? those bonds are quite strong, maybe stronger than we would have anticipated. And it's because those bonds are so strong that we're here to talk about it, right? It's because carbon-carbon and carbon-hydrogen bonds are things that all of the biological molecules are full of. And it's because those bonds are so strong and so stable that we can form these large molecules, right? Proteins, nucleic acids, carbohydrates, these really big molecules that contain a lot of information. And although I got some pushback from this, on this from my 2 classes earlier, I'll say the same thing to you, because I think it's true. I'm no cosmologist, but I take it from people who are that this is why nowadays I don't think very many people seriously think that if there is life on other planets in the universe, that it could be based on anything other than carbon. It seems to require carbon to have anything like what we would consider to be life as we understand it. Not silicon, even though there were, you know, all these science fiction movies in the 60s and 70s with silicon-based life forms. Silicon hydrogen bonds are quite unstable. You can get them. Those compounds exist. SiH4, for instance, happens to be called silane. I don't care if you know that. But it's the silicon analog of methane. Silane is stupidly unstable. If you exposed it to the air, it would immediately take flame and just burn up. Whereas methane, as long as you don't light a match to it, you know, it's quite stable to the air. The carbon-hydrogen bond is very strong. So I think that's sort of worth mentioning. Good, so I think, is that all we really need to say about bonds? So you're telling me there might be a planet full of human torches. Well, if there's anything that has silane on it, there isn't going to be human anything there. I can tell you that. It'll basically all turn to silica, and you'll have glass or sand or something like that. Good. So we'll review about how to draw structures and how to put the bonds in. I'm hoping at least to get, even if we just barely get to that point by 3:45, I'm hoping we get there today. We can pick up with that on Monday. So I've given you here the way I've always summarized for years how to draw Lewis structures. That does not mean that this is the best way to do it. I'm sure there's 1,000 ways I could have made it clearer, but it's at least a starting point. And now this is already in your class notes. And we'll get to drawing some structures. Well, why later on? Why not do it right now? Let's go to the whiteboard. And if I may, I'll get some ideas on which molecules. I never discuss the existence of aliens. You can discuss the existence. It's just that if there are any, they're most likely carbon-based, like we are. Good. Oh, well, we're doing formal charge next time. I don't like any one of those. I'll use another one. Let's say that we wanted to draw a molecule like CH2Cl2. And again, please pardon my horrible mouse drawing. I'll try to get, I'm pretty sure I have a stylus somewhere at home. I'll try to remember to bring it. Well, I'm just sort of showing how you can use the steps in the class notes. And I think that after you practice drawing structures enough, you won't need to have those steps close by. But I'll just kind of show you how they work. Generally, the least electronegative element is going to be the central atom. There are occasional exceptions, but when you look at a formula like CH2Cl2, I hope you're all thinking that carbon has to be the central atom no matter what, because hydrogen forms only one bond, and halogens like chlorine also prefer to form only one bond. So probably we want to put the carbon in the middle. The next step says to arrange the peripheral atoms around it in some relatively pleasing geometric pattern, assuming that you're not being asked to show the correct geometry of the atom, of the molecule. We'll just go like that. We'll just draw it as a flat structure. And when drawing it as a flat structure like that, you can put the H's and Cl's anywhere. It's the same thing. It carries the same information with a flat structure like this. And so, where was I? So next, what we have to do is we have to count the number of valence electrons total. Remember, we use valence electrons to form bonds. Again, I'm assuming you covered this in Gen Chem. That means when we add them up, that tells us how many electrons we get to use, and we also have to use all of them. So carbon has 4 valence electrons. You can tell just by looking at the periodic table and counting over, right? Lithium, beryllium, boron, carbon, 1, 2, 3, 4. So carbon is 4. Each of the 2 hydrogens has 1 valence electron, so that gives us 2 more. And halogens like chlorine, so this also goes for fluorine, chlorine, bromine, and iodine, they all have 7 valence electrons. 2 chlorines, 2 times 7 is 14. Okay, I guess this is a little bit of math. Sorry about that, it's arithmetic. I think we're okay. So 4 plus 2 is 6, 6 and 14 is 20. So that means we have to account for all 20 of those electrons in our structure, and we don't get to use any more than 20. So if you go down the list, then you'll see next we draw bonds between the peripheral atoms, each of the peripheral atoms and the central atom. Some of you might have learned to do like electron pairs in bonds as 2 dots like that. I am not a fan. I think you will confuse yourself less if you draw covalent bonds as lines. I can't say that's wrong. I can't in good conscience recommend it. I don't think it's a good idea. And I think you'll find when you work with OWL that, that it's the same thing, that they will draw those as lines. Good, so 2, 4, 6, 8, right? Each covalent bond is 2 electrons. So we've accounted for 8 of our 20 electrons. Doesn't hurt to keep track. 20 minus 8 is 12. That means there's 12 more electrons I've got to use. And you'll notice going down the procedure I put in the class notes, it's at this point that we use any remaining electrons as lone pairs to complete the octet. First on the peripheral atoms, and then on the central atom. There are atoms that are exceptions to the octet rule, like boron and aluminum. Well, like hydrogen, right? Hydrogen is only 2 electrons around it. But the carbon's fine. The carbon is 8 electrons around it, but the chlorines are not fine. So I think you'll find this will use up our 12 electrons. 1, 2, 3, 4, 6, 8, 10, 12, and we're done. So we've used all of our electrons. And so that's one of any number of correct ways to draw that structure. One thing that may make it easier, may make it harder, I never know quite how people will take this, but either way, I need to let you guys know, there are always many, many, many correct ways to draw any given structure. You know, maybe yours is turned 90 degrees from that, fine. I often will get questions like that. Again, you're never going to be graded directly on your structure drawing. You still should learn how to draw structures correctly. But like, especially in my 227 class, someone might say, if we drew that molecule turned around, would we lose points? And to some extent, I got to work on this. To some extent, questions like that kind of annoy me. But, and like I said, that's my problem. I need to work on that. But in a sense, it's not so bad because I get to say to that student, not only would I not take off points, but I wouldn't even notice. I would just look at it, observe that it's the same thing, and move on. So I think there's some information there that might be helpful. There's many, many correct ways to draw any given compound. Everyone's admiring my mouse skills. I don't know. Actually, it's difficult because normally I have to, this is boring, why am I telling you? Oh, well, I'm in it too far now. Normally I have to use the mouse with my left hand, even though I'm right-handed, because I get like repetitive stress stuff happening, but I write with my right hand. So you can be impressed if I can do that well with my left hand, but be that as it may, that's an example of working out the structure of a molecule. Let's maybe do one more. Oh, it's 3:30, so we have 15 minutes. Oh, let's do a fun one. CH2O. That, by the way, is something you'll have heard of. That's called formaldehyde. So the central atom in this case is carbon. It's not going to be the hydrogens. And oxygen is more electronegative than carbon. So we'll put the carbon in the middle. And I think you'll find that there are no oxygen-hydrogen bonds. if you tried, you'll find that you're not able to make every atom obey the octet rule. So I'll just let you know that now, but I'll just also let you know, if you'd been given this as a problem and you tried to attach an oxygen to a hydrogen, or a hydrogen to oxygen, you couldn't. You wouldn't be able to get a correct structure. This is the only way to line it up correctly. How many valence electrons? 1, 2, 2 and 4 is 6. Oxygen is 6 more, so we have 12 total. So first we'll connect our atoms with bonds. And so that used up 6 of our 12 electrons. That means there's 6 left. Now the rules state that we use any other electrons to complete the octet, first on peripheral atoms, and then on the central atom. We have 6 electrons left, so we have to use them to complete the octet on oxygen. Now oxygen is 8 electrons around it. However, there's a problem. What's the problem? Carbon only has 6 electrons around it. Now, interestingly, this structure here, as we'll learn on Monday, I think, is not entirely terrible. I don't think it's the best structure. In terms of that other thing, it would probably receive partial credit. At least it is the right number of electrons. If you worked it out, what you'd find is that the oxygen is a formal charge of -1 and the carbon is a formal charge of +1. So at least it adds up to 0. That's good. But the rules state that if we still lack an octet around the central atom, then, where's my eraser? Then we borrow an electron pair from one of the peripheral atoms to form a multiple bond. So that's where the double bond comes from. And that, I think, is the best structure. That or some variant on that where it's turned somehow, would be fine. So that's how multiple bonds come out. And I think we have yet to talk about, isn't water 2 hydrogens and 1 oxygen? Yes, but this isn't water, it's formaldehyde. So formaldehyde is, actually pure formaldehyde is a gas, but it's usually used as an aqueous solution, and they use that to preserve biological specimens. You all, I think, are familiar with the unpleasant odor of formaldehyde. And actually, we're going to do functional groups, I think, on Wednesday. And one of the things we'll learn about aldehydes in general, formaldehyde is the simplest possible aldehyde, is most all of them smell really disagreeable like that, with 1 or 2 interesting exceptions, which we'll get to. Not that it's important to memorize this, I'm just going to use examples like that to put it in context. Okay, good. So I think with that, we can go back to the class notes. I hope it's okay if I do that. I just want to make sure I don't really miss anything. We've already talked about electronegativity. We've already talked about the valence bond model. We've demonstrated carbon-carbon single bonds, both carbon-carbon single bonds and carbon-carbon bonds in general, and carbon-hydrogen bonds are quite nonpolar. Carbon and hydrogen don't have exactly the same electronegativity, but it's pretty darn close. It's almost, one is 2.5 and one is 2.1, and honestly, I can never remember which is which. If you guys just kind of remember, they're almost the same. I'm totally fine with that. So I don't think it's necessary to memorize exact electronegativity values. Now, that being said, I think being able to look at the periodic table and at least remember the trends for electronegativity, that's worthwhile. Don't bother memorizing any numbers, but I think it would be helpful for you to know that electronegativity increases to the right of the periodic table and it increases up the periodic table. So the most electronegative element you're going to run into is fluorine. That's at the top right, essentially, right? The noble gases don't count, they don't form bonds. So, and the least electronegative element that we will use might be potassium, might be cesium, it'll be one of those alkali metals. So yeah, don't bother memorizing exact numbers, but I think it's helpful to know those trends, just so you can recognize. A question on, I actually already closed REEF. I took attendance with it, but it didn't count for a grade. And it won't count on Monday either. The earliest I anticipate using REEF to count for a grade is Wednesday. I'm still learning how to use the system. So we learned that it can check attendance and it works. Awesome. Good. Electronegativity increases which directions again? It increases from left to right in the periodic table, and it increases up the periodic table. So fluorine is our most electronegative element that we're going to see forming bonds with other elements. And the more metallic an element gets, the less electronegative. Let's see, I think we've already sort of talked about valence, really. Multiple covalent bonds, well, I've already drawn a molecule with a double bond. Later on, we'll review about the presence of a double bond attached. A double bond to an atom means the atom needs to be sp2 hybridized, right? If a carbon atom is all 4 single bonds, then it'll be sp3 hybridized. And if there's a triple bond between any 2 atoms, it doesn't have to be carbons. The atoms can be anything. But if there's a triple bond, then the 2 atoms involved will be sp hybridized. And honestly, I think those are the only ones you're going to need for this class, sp3, sp2, and sp. And I think we'll talk more about that later, probably Monday. In Gen Chem, you might have covered some weird ones. You might have done like dsp2 or d2sp3. I don't think we're going to need those. Those only show up with transition metal complexes, and I don't remember drawing any for this class, so I don't think we'll need to worry about this. So if you can refresh your memories on sp3, sp2, and sp hybridization, I think we'll be in good shape. And like I said, I think we'll cover that more next week also. Good. So in the remaining 8 minutes or so, I think we've already kind of defined valence. It's the number of bonds that an atom can form, which, by the way, just let me show you. I've summarized that for you in the class notes. Did I just lie to you? I think I might. It should be in here somewhere. Maybe it's later in. I might have split it up and put it later. Oh, here we go. Yep. Here we go. So I've given you one of the versions of the formula to calculate formal charge, which also relates here. I don't think you'll really need to memorize that formula. You can if you like, but I think with enough practice, at least I hope, you'll be able to tell more or less by looking at an atom in a molecular structure, whether its formal charge is +1, 0, or -1. And I also don't think we're ever going to get any formal charges other than +1, 0, or -1. And furthermore, I think 99% of the time, or nearly so, the formal charge will be 0. So that's why I've given here what you can generally expect to see when an atom is a 0 formal charge, and also some common cases when an atom has a +1 or a -1 formal charge, respectively. And again, you can use this for now, you know, as a reference. But I think after a while, you'll learn the patterns. At least that's my hope. Actually, I see that's in 1.11, so technically that comes later. But it is relevant for now, since it's not always possible to go exactly in order. But I'll get back within the lines over here. Good. So all that being said, that relates to valence, and that valence tells us how many bonds a given atom can form. That's why I think it's good to be able to count to 4, so you know that a carbon has 4 bonds. Good. Now, that also gets us to the idea of isomerism. And there are few different flavors of isomers. But in general, for now, and I think we'll end with this today, we just need to get down that the type of isomerism that's called structural isomerism or constitutional isomerism is this phenomenon of having 2 or more molecules that have the same molecular formula, but the way the atoms are connected is different. They have different structures. So if I could go back to my whiteboard, just a moment, new share, whiteboard. I'm getting trained here. I'll figure it out sooner or later. Let's say that we took a formula such as C3H8O. Those are some pretty poor numbers. C3H8O, we'll go with that. Well, you will find that there's many different isomers. So you could connect the 3 carbons all in a straight line, or all in a chain, I should say, and then put the oxygen on the end. The oxygen will have the hydrogen, will have a hydrogen attached, let's say. We've got lone pairs on the oxygen, and we need hydrogens to complete the octet and all of these other carbon atoms. We want them all to have 4 bonds. It's getting a little tedious, but we'll finish the class well enough. That's a bond, sorry. Good, and I think that's 8, that has to be 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, yep. So that's one way. Now, what about this? This is a little bit tricky. Oh, let's even go like this. That's a carbon, sorry. Well, don't be too impressed. I do spend most of my life on the computer. Don't you? I mean, when you're having free time, what are you doing? Watching YouTube, right? You know, I'm the same. So what about that? I admit it's kind of a trick question. Because these two are the same molecule, right? The same atoms are attached the same way in the same order. I've just flipped the molecule around. So those are not 2 different compounds. Those are 2 different ways of drawing the same compound. And that then gets to the question, is there anything we can do to make this less tedious? Thank goodness, yes. We'll get to that on Monday. We'll start talking about ways of abbreviating structures. I do want to, before I get to an isomer of this, I do just want to warn you guys off of, granted again, you're not going to be graded directly on structure drawing, but I see a lot of this where people just put sticks and don't put H's. I'm not a fan. Granted, as I said, I'm not going to be grading your structures directly. I would advise against it. I think there might be one OWL problem where they force you to do it, but I'm not a fan. Put the letter H's in, you know. I think it will avoid confusion. There are ways of drawing structures of abbreviated that you don't have to go bond H, bond H, bond H ad infinitum. So there are ways of doing that we'll learn on Monday. But just putting sticks in, I don't recommend it. I'm not a fan. So let's see if we can find another C3H8O. I'm gonna take advantage of clearing it because once it's on YouTube, you can pause it. What if, let's say, we put the oxygen in the middle of the chain? That's certainly allowed. Sorry. If our tests are all online, how will you ever see? It'll be multiple choice. So I won't be grading any structures that you draw. When is our first OWL assignment? Nothing will be due before a week from today. That will be the very earliest. I'll take a look over the weekend. But certainly nothing before then. Bond H, bond H. Okay, so I think you can see that's a different structure. The other oxygen was attached to a hydrogen. This one's not. This one's between the carbons. So that's a different compound. That's a constitutional isomer of what we drew. Later on, we'll learn that the first compound we drew was called 1-propanol, and this guy, I guess you could call ethyl methyl ether. We'll learn our functional groups next week also. And by the way, you'll notice if I'd written CH3O, CH2, CH3, again, it's the same compound. You've just flipped it around. So that's going to be something that requires practice, and I'm confident you'll get plenty of practice with that in the OWL assignments. So like I said, I'll try to get at least something up this weekend, and nothing will be due before a week from Friday. Did I tell you that OWL assignments will generally be due on Fridays? Did I go? Yeah, because I tried Mondays at first, then people wanted to push back to Tuesdays and Wednesdays, and finally I said, let's just do Fridays. That way you get it over with for the weekend and you can do different things in the weekend. And I am out of time. So yeah, OWLs will do Fridays first, no earlier than a week.